barely explained it. We put it on the board and that was it. Did you guys write down the squeeze theorem?
No.
You don't have to memorize it.
You have to write it down.
But still, it's an important one.
Okay.
I get to faster. The one too faster.
Yeah, class was ending.
Now, why? Pourquoi? Why aren't we just using the limit as x goes to 0, 1 minus cosine of x over x is 0? We can't. Because where are we approaching?
Infinity.
Okay. So, what do you think one of the most common, if this is on the AP test, one of the most common mistakes is?
0.
Thinking it's going to 0, right? That's common mistake number 1. But now that we notice it's going to infinity, how do we, is my phone actually plugged in? Yes, but then I started texting, I was checking my text messages. Senior student council stuff. Go team. The squeeze theorem allows us to see if we can determine a function that is always greater than and always less than, well, always greater than or equal to, and a function that's always less than or equal to, and see if they converge to a particular limit. And if they converge to a limit, they squeeze the function in between to that limit as well. What do I mean? What do we know about cosine of x? We talked about this yesterday. I just want to develop it.
It's under. It equals 0 at pi over 2.
That's one fact. What do we know about the entire function? What is it contained by?
1 and negative 1.
1 and negative 1. So the function value, domain is all real numbers, and it is sinusoidal, and it's periodic, and all that stuff. But it's contained within 1 and negative 1. So if it's contained within 1 and negative 1, can I say, mathematically, that 1 minus cosine of x all over x squared has to be contained within, Can you guys figure out what two functions I'm going to use that are much more basic and don't involve cosine?
Sine.
No,
Because a limit to infinity of cosine or sine are both problematic. Because they technically don't
1 over
exist.
x probably then.
True, but if it's 1 minus negative 1, it's
2.
not contained by 1 over,
So it's 0 or 2.
not 0.
So, what do you think? Yeah, because if it's 1.
I should have said, sorry, not 2. 2 over what?
2 over
X.
x.
Okay. No, 2 over.
X squared.
And then on this side I could say,
0.
right?
Oh,
And what are you thinking? You're thinking cosine can be all the values between negative 1 and 1. So what if cosine was the lowest? It could be negative 1. It'd be 2. So it can't go beyond 2. And if cosine was the highest, it could be 1 minus 1 is 0. It can't go below 0. True? Okay. So if we were to take the limit as x goes to infinity of 0, what would we get?
as a 0.
The limiting constant is itself. But what if we were to take the limit as x goes to infinity of 2 over x squared?
0.
Squeeze theorem says, well, if his limit is 0 as you go to infinity, and his limit is 0 as you go to infinity, guess who's squeezed in between? So the answer is 0. Now, how can we think about this without doing that work every time? Now, that work is possible, especially with sinusoidals, because sine and cosine, as you go to infinity, or even tangent secant, how do you describe what's going on? Because it oscillates. Well, it oscillates sine and cosine between a fixed interval, so we can think about those fixed intervals to help us know what it's bounded by on either side. But the other way of thinking about it is just in context, and this was our shortcut last year. Which one's stronger, top or bottom? Bottom. Because bottom goes to infinity, top is stuck. Without even thinking about where it's stuck, right? And since it's stuck, the bottom is getting bigger faster, so hence yes here. But just wanted to demonstrate how the squeeze theorem works, and I think I gave you like one problem on there.
Yeah, there's just one.
Okay, cool. That has you actually work through that process. And it's pretty similar to the one I did.
Miss D, for that one I just
Give
put.
you this one?
I think it might have been this one.
Yeah, it was this one. Miss D, for that one I just did the negative 1 is less than or equal to cosine of x, which is less than or equal to 1 over infinity. So I just put 0.
No, well, logically you can think through it that way. I was showing why that works, because technically the limit of cosine is dne over infinity. Well, how do you resolve that?
You can put anything over infinity, 0, I guess. No?
Infinity over infinity doesn't work. And 0 over
Wouldn't it be
infinity,
just 1? Anything over itself is 1?
No.
Why?
because 0 over 0 doesn't work. So
Okay.
0 over 0 is indeterminate, infinity over infinity is indeterminate, because infinity is an idea. But if you just look at infinity, do you truly know which one's stronger or not? Or whether they're actually tied or not? You know they're both going there, but some go really fast, some go much slower.
Mhm.
Does that make sense?
Imagine it.
Okay, let's keep going. We talked about, don't write, you're fine. We talked about this yesterday real quick, just the sense that it does exist. Remember, these are not derivative rules, these are limit rules. But the sense of we can think through separately, and that's what we've basically been doing the whole time, so don't stress, I just wanted to, that's the thing. However, even though these are pretty self-explanatory, right? It's like, if I have x squared minus 5x, hey, just take the limit of each. Or if I have 1 over x minus, etc.
Wait, can we write that last one?
Oh, do you want to?
Yeah, because I haven't seen that before.
Oh, to a power.
Mm-hmm.
And remember, hey, this is just a quick review that always gets confusing. What's a more logical way of writing L to the R over S?
The root
What root?
of S
R root. Oh, sorry, S root.
to the power of f of x.
Right? Just a quick reminder. It's one of those that just gets tangled as we get more time from what we're actually supposed to be doing. Okay, can I keep going now? No. A little bit longer.
I just need to see some information.
Okay. Technically what he's writing at the bottom, it says, provided that L to the RS is a real number and L is greater than 0 if S is even. We basically just can't take an even root of a negative number, right? That kind of makes sense. Real number can't have complex, that kind of makes sense. Let's go up to the quotient rule. The denominator can't equal 0. Does that make sense? We're not going to spend tons of time on this next page, but I did want us to at least think through it. Because the book totally mapped it out to be an exploration for us. So take number 1. We have f, we have g. So write out the function, the limit as x goes to infinity of f over g, or 5x plus by sine of x over x.
What is theorem 5?
Don't you re-
Is that big old
you need
huge
to
page on the
record
page?
that?
Huh?
You're recording it.
Oh, thanks. I was blocking it. So for number 1. You guys don't have to write all the words. We're just writing this down, right? What they're having us kind of grapple with is what I sort of had you grapple with on the last page, in the sense of, can we take the limit as x goes to infinity of the top?
On the top?
No.
Because it's bounded between.
Technically, no. Of the bottom, yes. So then it says, can we apply the quotient rule?
No.
The quotient rule says, take it of the top, take it of the bottom, and compare.
Well,
Top is D.
Top is D and E, bottom is infinity. Well, how do we grapple with that? We don't. So does the quotient rule technically work?
no.
No. But does the limit of the quotient exist?
That's
Yes, it does.
But what is it?
can we use
5.
How?
Because the powers are equal.
what?
The sin x is, I believe, relevant.
Who wins when you're thinking about the degree? This is a shortcut way, right? It's not very mathematical. I'm not showing proof necessarily. But technically, does sine win or does x win?
X.
X wins, because x is linear, sine is just stuck, right? So then if x wins, now compare, oh hey, they're tied, so therefore the limit is 5. What's another way of looking at that?
You have to check the sign? No.
We could, but since it's positive infinity, sorry, I checked it fast.
Okay.
Positive over a positive. Couldn't we also just split up 5x over x plus sine of x over x? Couldn't we always do it that way?
Yes.
Maybe a little bit easier. So 5x over x, Hart method, plus sine x over x.
So it's
Or
sin-
distribute 1 over x to both pieces on top.
Well, what's sin x over x?
0.
But that's only that. That only if you approach 0.
No. This is actually 1 if you approach 0. By the special trig limit. Why is it 0 as you go to infinity? Same thing, because this would be held within 1 over x and negative 1 over x, squeeze it in. 0. Or, better way of thinking about it, who wins, sine or x? X wins. So bottom wins, limit is 0. Yeah?
Miss T.
Uh-huh.
For the limit as
You guys go on to number 2.
the limit as u approaches infinity of 1 minus cosine of u over u, what would that be?
That's the one we just did on the page before. That one's the one that's held within 2 over u and 0 over u.
No, but that one was x squared on the bottom. And x on top.
True. But the way you said, I was saying it's like that one in the sense that it'd be 2 over u, just not 2 over u squared.
Mm-hmm.
And 0 over u instead of 0 over u squared. But still, what does 2 over u approach to infinity? 0. What 0 approaches you go to infinity? 0.
So 0?
Which makes sense once again, cosine is restricted. U and the bottom is not. Bottom wins, bottom is stronger, limit is 0.
Isn't 1? Is that like
The limit as x goes to infinity is trying to show us exceptions that we have to watch out for, right? Because if we just plug in
It's 1.
sine squared of infinity, it doesn't exist, except we know that this is a set constant, it's a Pythagorean theorem, so therefore, since this is 1, the whole thing is 1, right?
Yeah.
So keep an eye out for trig properties. What's the third one? Don't worry, work it out. Work it out, work it out. It's mostly just asking the question, can you figure out how to solve them? And remember, guys, we do have a lot of tricks to these. We're not proving necessarily. College professors might be a little mad as to how we're doing them. But for the AP, we have to simplify. Shorten the time we take, right? If you go on in college math, they'll be like, but why? And that's where the rub comes.
Well, you are explaining us at least why and how.
Somewhat. I'm describing. I'm not proving. Proving would be, go back to Danny again.
Danny Keegan.
I'll tell you all about what proving is.
Didn't you take a class you have to prove basic addition?
Yeah.
What was it like?
Prove that a real number plus a real number is still a real number. That addition is closed under, no, that real numbers are closed under addition. I said duh, everyone else wrote like pages and then
You said That's
I
fine.
thought duh. Oh well. E for effort.
Did you
So,
pass that class?
Of course you did. It's Miss T.
did I what?
Did you pass that class?
Did kind of make me change my major though. I didn't like getting B's. So, F. I almost dropped it so I wouldn't get a B. That's how lame I was. Talk about pride. Struggle.
YOLO.
And then I stayed and I took the B.
No.
I got another B. Because I was working too hard on that one. Well, and this slacker girl who was working her way through college, and that's to be commended. She didn't hear you, YOLO. I said it. Okay. What do you do? Infinity minus infinity, it's impossible.
0.
Combine it.
Combine it, because it's a logarithm. You can't do infinity minus infinity is 0 because we don't know the degrees of infinity. True?
True.
Fine.
That's
I
called
thought that after I said
indeterminate. Infinity minus infinity is indeterminate.
And then the
I just wrote ln, that's funny.
I like it.
So, what would it be?
2x
2x over
minus,
x
or
plus
2x over x plus 1.
Now what?
And then the top wins, or the top, they're equal, so ln of 2.
Ratio leading coefficient?
So then a constant is a constant, and 2.
Wait, what?
ln of
So,
2.
Wait, why is it 2?
Because we go within and we say, hey, they're tied. Composition of functions, we can pull the ln out, we can look at the inside, say that ratio leading coefficients is 2, bring the ln back in, ln of 2 is our final constant. Constant answer.
Is it kind of like chain rule?
No. No, do not compare. Nope. Gerardo, it's like property number.
Next one.
It's not even in there.
Oh, it's basically like.
It's a property.
Isn't it like?
It's a composition property.
The power
So the
rule.
limit of f of g of x is the same thing as f of the limit of g of x.
True.
Sorry, I thought it was there. Maybe it's another random theorem I didn't think was important. Okay. Infinite limits. Oh, so their question was, what do we have to say then about all of these properties?
They're gangster.
They're not always true. Or they don't always
There are some special cases where we get an indeterminate answer. So indeterminates have to point us to keep looking. Like we already know. But we're used to 0 over 0. But now we have things like dne over infinity. Well, what's that? I don't know. Keep thinking. Or infinity plus infinity. Is that truly? Not infinity. Sorry, dne plus dne. Well, what does that mean? Or infinity minus infinity. What does that mean? Or
That's it.
that's it. The end. Okay, so we've been talking a lot about horizontal asymptotes, hence the limit as you approach infinity, but what else is in this section? The limit as you approach a constant where the function goes infinite.
Bum, bum, bum.
Dun, dun, dun. Vertical asymptotes. Take a second. Think, digest, ponder, reflect. Get it done.
Are we gonna be allowed to sit on the floor during class?
George, you can do that any day you want.
Yeah.
Don't hurt anybody.
Is that a fat joke?
No.
Why do you always say that?
Because it seemed like a fat joke, Gerardo. Okay.
Depending on where you sit,
It may be a
it
fat joke.
may be inconvenient. And it may also get very uncomfortable from time to time.
It's harder to write and read your back.
How do you don't have a back?
That's true.
I'm not sure if we're spineless.
I don't think you can sit up if you're spineless.
According to Coach Stay.
He called you spineless?
Well, he calls me pansy sometimes.
Whoa! Is that even legal?
I think it is.
Football coaches can do that kind of thing.
Just because you're okay, fine.
And you try telling Coach Hurst not to. Joyce is hearing my sob story.
Joyce said she liked our stories yesterday.
Did she really?
Yeah.
The one about infinity and fidelity?
Yeah.
Okay.
And how awkward we are when we say hi to her.
I hit
The
Joyce
sad
in the
thing
head with my
was,
locker
yesterday
by
it was
accident.
pretty good, except then I restarted it, and then it was the awkward forced.
Joyce.
But yesterday you guys were totally like, hi Joyce, as you were writing, like you were just totally nonchalant. Today
Well,
was
some of us were,
Mhm.
and there was other of us.
Joyce, there was a pause in between the time before Ms. D said yellow and the time after that, in which she told a story.
Thank you for letting her know, because that was Misty's point, right?
It wasn't to keep it from Joyce, it was just to keep it from being on the internet.
Recorded.
That's why I didn't say the story.
So you're telling her to ask me later.
So we're not blackmailing Ms. D. Joyce won't find out about this until like
Wait, Misty,
tonight.
how come you don't go grade the... Oh, wait, never mind.
I'm gonna find out about it next week. What?
I was going to say grade the AP tests, but I think you told me before.
Because mission trips are always
Yeah, that's what I thought.
Which this year it might not be. But I needed to have like applied a while ago for this year.
Wait a
I
minute.
didn't know it wasn't gonna be.
If you did do it, would you do it in your what's it signature blue pen?
I would do it whatever way they told me to.
And she take mine and give me a 5.
Yeah, there's not even names on it.
I know.
So you'd have to
she
make it
thought I'd
obvious,
give you my
and then
code.
I would have to happen to be the one person in the whole room
I'd give
grading
you my
that question.
code and you'd be trading around.
And I could only grade one question, not your entire FRQ packet.
That's
so
fine.
that
I'll
would
take
be-
a 9 on just one for sure.
Okay. Vertical asymptote, that's its technical definition. True, true, true.
Vertical asymptote.
But how do we analyze a function to know whether it's going to positive or negative infinity as it comes in towards a vertical asymptote?
Check the zeros at the bottom.
Check the sign.
Well, that tells us there is a vertical asymptote, but how do we know whether it's positive or negative infinity?
Check the sign.
Check the sign. Oh,
Check the sign, but how? So the limit as, let me get you one and then Gerardo will go.
Oh, let's go away.
As x approaches,
2. Or how about just...
4. Oh.
Snap. Oh, come on, George, you're not that bad.
Ready, set, go!
Go.
Gerardo, what was your question?
I just wanted to give one.
It's relative. Well, that's a number of 0.
What number over 0?
I don't know.
Oh, come on!
Is it like, I got this root.
Where's pi over 6?
That's
30.
Good. 1/2.
Yeah. Little problems why you're asking for nothing. Yes, Joyce, they really.
Uh-oh, that's a number over 0. If it's a number over 0, that means there's a vertical asymptote at x equals pi over 6. But what is the dilemma that we now have to face? That's not the answer. That's just an explanation of what we see.
Does that mean it goes to infinity?
Yes.
But how? It
Well,
can go to infinity in an agreeing way up or an agreeing way down or a disagreeing way, hence DNE.
check the both either side.
How?
Low to the right, low to the left.
Little to the right, little to the left. So limit as x approaches pi over 6. Little below. Limit as x approaches pi over 6. Little above. Without your calculator.
So that would be like 0.
Yeah, 0 and pi over 3. I would just make it
0 and pi over 2.
Oh, you know what? Yeah, that's even easier. Good one, George.
Or is that too far above and too far below?
It depends. I would just go really close. Meaning, what is sine entirely in the first quadrant? Because pi over 6, a little before, a little after, is still the first quadrant, right? So it's positive, so I have that. A little bit above, no, a little bit below pi over 6. A little bit less than pi over 6. Well, when I subtract pi over 6, what do I get?
0.
But a little bit below pi over 6.
Oh.
No.
I get a negative.
Wait, what?
Because you're subtracting
Oh, because it's
a
Yeah.
bigger number.
Yeah.
Does that make sense? You don't have to know the exacts. We just need to know the sign. Check the sign.
Yeah.
So as I come from below, it'll be negative infinity because it's a vertical asymptote. As I come from above, well, top is positive. The bottom is a little bit bigger than minus it. It'll be a positive. So hence my entire limit in this case.
DNE.
So vertical asymptote is what is going on when I get a number over 0, true? Just a reminder, number over 0, infinite form. I think we already talked about it the other day, but that's okay.
Misty, so you said that sine of x from a little bit to the left would still, a little bit below, would still be positive, right?
Mhm. Because remember, I mean, we could go down to the 4th or go to the 2nd, which would still be positive, but we need to zero in on right before. So we're approaching and getting closer and closer and closer, so we care about right before. Okay, let's keep going. Now this is a little different. End behavior models. A little different terminology. The idea is still important.
I got to that part in homework.
Nice.
I kind of just wrote a sentence as to why it goes this way and that way. So,
Kind of works.
good for you.
The wording and behavior model will definitely not be on the AP. However, it does kind of give some explanation behind what we do, why we do, etc. In the sense of why we can just look at the leading coefficients. Another reason, I should say, perhaps. Because we can multiply top and bottom by 1 over the highest degree. We should be able to see it that way as well. I think that makes sense. So you're given a beginning function, and from that beginning function, you're trying to figure out what simpler function behaves as you head to the right towards positive infinity, as you head to the left towards negative infinity. Which function behaves the same way? In theory, to be able to help taking limits be easier once again. So for instance, if I was to give you like this one. Let's go. the function x squared plus e to the negative x. And if we're trying to find a simpler, because right now this is the addition of two very different functions, and if we're trying to think of what would be, which one comes first technically in homework, is it left? No, right. A right end behavior model. Remember, the name of the game is simpler. And a left end behavior model. It's like an application of limits to infinity. I'm putting my words together. Right end behavior, what am I kind of thinking about? The limit as x approaches positive infinity. That's what I'm going to be contemplating. And then as I go to the left, the limit as x approaches. Okay, those are what I'm kind of like using in order to be able to find this. So we're trying to identify the model, hence we're trying to identify the function g. Okay? Another function, a simpler function. Now, as we go to positive infinity, which means we're not zooming in the middle where like x is between negative 100 and 100. We're talking about beyond that. How is this function behaving?
Well, it's x squared.
The x squared is just doing his thing.
And
Plus,
the e is being dampened.
Yes, because e to the negative x means 1 over e to the x. And e to the, as we go to infinity, that's getting huge, which means that entire quantity is going to 0. So what would the end behavior model be? He has no power at all. And if we were to graph this function as we go to the right, it's going to end up looking like x squared because e to the negative x is not changing it much. And as we get closer to infinity, it's going to be affecting it less and less and less and less, like infinitesimally less. So then similarly, think the other direction. What if x was approaching negative infinity?
Then it would still be...
X squared's doing his thing.
Yeah.
What's going on with e to the negative x, though?
It would be 1 over e to the negative infinity. It would still be 0.
No.
1 over e to the negative infinity
E to the
would
infinity.
be e to the infinity. Who's taking over?
E. I thought that at first, but I thought no. So it kind of just undoes the negative kind of undoes itself and it just becomes.
Because you can take
X on
e to the negative of negative numbers.
Oh.
Bigger would be e to the positive.
That's what I was
And
thinking.
x squared is doing his thing, but as we go to infinity, e is so much stronger, he takes over. Does that make sense? So it's kind of like whose magnitude is ultimately running things as we go. So that's what's going on with right and end behavior. I thought that was an interesting application we hadn't really specifically talked about before. And of course, as we zoom in the middle of the graph, they're going to be very different graphs, but as we go out, looking at the end behaviors.
Wait, that on our last slide, the g of x equals e to the infinity? G e to the x.
E to the x specifically. We're just thinking about the limits to infinity to be able to inform our analysis of the function. Does that make sense?
The end behavior will look like that. Okay.
I think this is the last slide-ish. And ironically, we kind of come back to number 17 from yesterday.
That.
But not immediately. So hold on.
An elusive number 17.
So seeing, in quotes, limits as x goes to infinity. There is obviously what we've been doing, which is thinking about the degrees in the top and the bottom, who is stronger, who is not. Technically, L'Hopital's can still apply if we get infinity over infinity. Because infinity over infinity is indeterminate as well. Same problem with infinity minus infinity, which degree is stronger. Same thing applies with subtraction. Is it truly 0? Is it something else? But there is another way of looking at limits, which I thought was interesting as well. And so I wanted to show it to you. Not to say that you couldn't think through either of these, but to say there's another way of thinking through.
Do we need to know the epsilon and delta definition of limits for the?
No.
Thank God, that was confusing.
It's helpful for college math. but for the AP specifically, no. There's not really a good way to test that, I don't think. And the AP is not necessarily as purist as probably some college professors would wish it was. Okay, so number 1. You guys wrote the other way of looking up above, and we'll get to that in just a second, but let's just think normal. You're given this question, number 1, the limit as x goes to infinity of sine of 1 over x. What would you answer?
Sine of 0, 0.
Sine of 0 is 0, and that is the answer, that's true. But what is another way of looking at it? We could look at the limit as x approaches infinity of a given function as, instead, as long as it exists, the limit as x approaches 0, but going to positive infinity, 0 from the right, of sine of the reciprocal argument. It's going to be the same thing. Why is that helpful?
Because you just put it
Oh.
to 0.
Sine of 0 is 0, whether coming from the right or the left. I gave this one as an easy one because hopefully you could look at it and be like, oh yeah, 1 over infinity, that's going to 0, sine of 0 is 0, done. And similarly, limit as x goes to 0 from the right of sine of x, it's just going to 0, done. But what about the second one? What can we similarly say? What can we similarly say
It's going to
about this one?
Oh, it's going to 0. My bad.
It's kind of like the converse.
Can you do it if it doesn't have a plus or a minus?
Inverse? Well, that's the dilemma. What would we have to do technically?
2. And do we take the limits separately?
Mhm.
It would be the limit times the limit, right?
Well, hold on. How could we think about them? Because remember, we can think of the limit as x approaches 0 of as the limit as x goes to infinity of the reciprocal, and we can think of the limit as x goes to infinity of as the limit as x goes to 0, the appropriate sign of the reciprocal argument. So what's going on here? Equals the limit as x goes to positive infinity. And similarly down here, limit as x goes to negative infinity of
It's, no,
X sine of 1 over x?
1 over x.
Sine of x.
and similarly. And we've already talked about this one a couple different times today. How do we think through this function? X on the bottom is stronger. Sine is still confined, no matter which direction you go. And since those two agree, here's another reason, Gerardo, why we can say the limit is truly 0. Now, something I didn't actually show yesterday, but does make sense.
Why do you, so that thing says to flip the arguments?
Yeah.
And x is the arguments, f of calc.
But couldn't we also look at this as, I don't remember if we actually did this yesterday, sine of u over u?
Oh, snap.
But why doesn't that work? Hold on, wait.
Because it would have to be as x approaches
0.
nothing. Because you can't get
Remember, sine of u over u is only the limit as u approaches 0, right?
and you can't get u to approach.
Oh, we can't get u to approach
To
0.
get u to approach 0, x needs to be approaching infinity. Does that make sense? Because if x approaches infinity, then 1 over x approaches 0. So if the limit as x approaches infinity, that would be 1. So then how do we do it yesterday? Sine of infinity was confined. 1 over x was not.
You just kind of, you said we talked about it.
Are you talking about squeeze thing?
No.
This didn't work. It was one way of looking at it, but x would need to be going to infinity. So that's not so hot.
Wait. Couldn't you just, no.
But can't I just think about them separately and say sine of 1 over 0 would be sine basically going to infinity. And as sine goes to infinity, it still cycles in between 1 and 1.
1 and negative
1 and negative 1. So we could use squeeze theorem to say this is going to be in between 1x and negative 1x. And what's going on with negative x and positive x as x goes to 0?
Getting closer and closer.
So we could use this way to solve it, or we could use this way to solve it, the squeeze theorem, or something similar to say sine is confined between 1 and negative 1. What's going on as x goes to 0? Well, 0 times all those different quantities between 1 and negative 1 are always going to be
Wait, why is x
closer to
just
0.
still x?
Remember sine goes between 1 and negative 1? So the highest I can have sine be is 1. 1 times x will be the upper bound. Sorry, or equal to. Is that what you're asking? I apologize.
Not just that, but it's just like, if they're going to 0, wouldn't you have to take the limit separately?
Put zeros in between.
Yeah, but anything times 0 is 0.
Yeah, but the limit as x goes to 0 of negative x is 0. The limit as x goes to 0 of x is 0, so they squeeze the one in between. It's going to 0 too.
Okay. Because all you can get out from that function is those two values.
Well,
So
everything in between those two values.
everything in between those two values.
So
And
if
if-
1 is the highest sign can be, 1 times x will be the upper. And if negative 1 is the lowest sign can be, negative 1 times x will be the lower.
And it's because of the limit to 0, but both 0. So those are the bounds, as if the bounds were two different functions.
Squeeze function, or squeeze theorem. So take the limits of these two functions, since they equal 0, they squeeze that one in there as well. Jordan.
If the limits of the bounds did not equal 0, or if one of them equaled 0 and one of them didn't, would it be D and E?
I need to pick a better function to squeeze.
Okay, so like it's not D and E automatically, it's just
Right.
it's just
Right, it just means that we didn't pick the functions well. And to be honest, on the AP that I've seen, they don't necessarily, ever mention the squeeze theorem or make you use the squeeze theorem, but it could be a strategy to solving weird limits they might throw at you. Does that make sense? And especially when thinking through science. Hey, we're done! Homework number 4, section 2.2. Some of you guys started last night. Do we have any particular questions?
Let me
Yeah.
check. Let me check.
If not, I have one more thing we can do. I'm just offering my assistance.
For the vertical asymptotes, you can have multiple, right?
Yes. Multiple, like for a particular function, not
Yeah.
additive.
30,
Uh-huh.
30 and 33 say describe the behavior of f of x to the left and right of each vertical asymptote. I kind of just wrote sentences at x
So the
equals.
left and the right means from the left and the right, in the sense of is it going to positive or negative?
Yeah, I put at x equals negative 1/2, the left goes to 0 and the right has a 0. And at x equals 3, this is 30.
Wait. If it's a vertical asymptote, hold on.
Because it's got a 0.
You're thinking to negative and positive infinity. It's asking, given a vertical asymptote, right to the left, what's going on? Where's it going? So from the left is a better way of maybe interpreting what they're asking.
But from the right,
It has to, if it's a vertical asymptote, it has to be going to positive or negative infinity,
or
unless it's a piecewise function.
from the right, it would be going to negative infinity.
Okay. So it can't go to 0.
Oh, I was thinking I'm going to the right that way.
Yeah. See, you were thinking
As it
to
keeps going.
the, instead of go to the right and then come in.
Yeah. I was thinking to the right, not from the right.
Yeah. Anything
Yeah,
else?
Is
Okay, back to your spirals. Do I have them ready? I can get it.
wait, no.
Oh, I don't. Where are they? Yeah. Try the 3 multiple choice.
I feel like these are gonna be the best.
There's a free responsey thing at the end, but just try the 3 multiple choice. We don't have time. We'll do the free responsey thing at the end. Back of your spiral, put section, or whatever, quick quiz for AP prep. They have them every now and then. You just do a quick quiz. Quick AP quiz. AP prep, I don't care. Try multiple choice 1, 2, and 3. Technically, I have enough AP time to do 1 or maybe 2. So try to get 1, maybe 2 done before the bell. You can get all 3. That's awesome. Can you read it? Hold on, something's.
So 2 from the right.
We're gonna pause for a second. Whatever you didn't get to, we'll look at tomorrow. But number 1, what'd you guys get?
I got D.
Nice. Number 2, what'd you get?
A.
What?
Yeah, A.
Because 2 from the right, maybe you didn't see it. Plug it into the second piece.
Oh, I wrote the less than greater than wrong.
Oh, there you go.
Not really.
All right. Beginning of class tomorrow, we'll have the next 2, the multiple choice and the free response. So back to your spirals, we'll start, then we'll do your homework, then we'll keep going. Good to go? All right, you guys can say bye.
Bye, Joyce.